The next part of our kinetics chapter deals with reaction mechanisms, looking at a rate law. Rate is equal to K times the concentration of our reactants raised to some order, and using that information to try to develop an understanding of the pathway in which the reactants took to reach the products. The process by which a reaction occurs is typically called a reaction mechanism, a multi-step process in which reactants collide to turn into a product. A reaction mechanism is a pathway. Each one of those elementary reactions, when added up, will create the overall equation we're used to seeing, left equals the right. However, there is an activation energy for each of the elementary steps along the way. And remember, it's the activation energy, that energy barrier between the reactants and products, that determines the K, the rate constant. And according to Arrhenius, we know that that rate constant is temperature dependent, that the frequency factor raised to negative EA over RT, where EA stands for our activation energy, the barrier between reactants and products. R is the gas constant in the metric unit 8.31, and T is the Kelvin temperature. So the rate constant varies with the increasing or decreasing temperature. As we look at a pathway as reactants turn to products, we get great insight when we look at the activation energy curve. Let's suppose we have energy on an XY axis, and I'll just label on the y-axis this is energy, typically measured in joules, and on the x-axis is time going by. As time goes by, reactants turn to products. Let's suppose we look at an energy graph in which we see three different energy barriers. So here will be the initial reactants. We'll just start them at about this level on our XY axes. And I see the first energy barrier, and then it comes back down. Then I climb a next energy barrier, and it comes back down. And then a third energy barrier, and it finally reaches the end in which we have our products. I count 1, 2, 3 different energy barriers. This is giving me insight into the reaction mechanism. This must have occurred in 3 elementary steps. When reactants turned to products, it took 3 different collisions with the reactants forming intermediates along the way. In this first energy barrier, we could list from the beginning of the reactants to the top of that hill the activation energy for our reaction 1. This would have a value known as K1, the rate constant for the first elementary reaction. From the reactants all the way to the top of the second energy barrier, we would have the activation energy for the second elementary step, and this would have a rate constant known as K2. And again, in the third elementary step, all the way back down to the reactants, we would have a third value of the activation energy and a third K value for that third elementary step. When I look at this particular energy graph, reactants form products over time. It looks like that it took 1, 2, 3 different collisions, 3 different elementary steps for the reactants to finally achieve the overall product. Each time we have a collision in an elementary reaction, we produce something known as an intermediate. An intermediate is something that is made by a collision but then gets used up in the next step. An intermediate gets made but then immediately used. So we're looking at a reaction mechanism really as the pathway that reactions follow to achieve reactant-product overall equations. It's a series of steps that actually occur in a reaction. Kinetics tells us a whole lot about the mechanism. Understanding the elementary steps allow us to predict reaction pathways. Oftentimes when we see a balanced equation, it doesn't tell us how the reactants became products. For instance, in this equation, we have 2 molecules of NO2 combining with a molecule of F2. 1, 2, 3 total molecules on the left. And I see on the product side, they've rearranged to form 2 molecules of NO2F. If I look at this particular reaction, just visually for a moment, a molecule of NO2 could be represented with this figure. A second molecule of NO2, and finally the F2. There are 3 molecules on the left side of our equation. How do they achieve the overall product, 2 units of NO2F? Do all 3 of them collide together and magically turn to the product? Do I have 1 molecule of NO2 colliding with an F2? Do I have both of these molecules colliding together and then in the next step collide here? What we're trying to do is predict, looking at the number of collisions, how can we use kinetics to give us insight into the order in which these molecules collide to give us the desired product? If I were to look at 2 NO2F and F2 and the way that they collide step by step, we would develop what's known as the reaction mechanism. If this rate law that is observed shows rate is equal to K times NO2 to the first order and F2 to the first order, that rate law gives us great insight into what's actually colliding. Notice that the stoichiometry does not give a role, but what it's giving us insight to is what's actually colliding. By looking at this rate law, I would predict that a molecule of NO2F in a first elementary reaction has to collide with a molecule of fluorine. There is my first collision. Remember, at the top of the activation energy, we get this intermediate. At the top of the barrier is an intermediate. That's where bonds are breaking and new bonds are forming. We're rearranging to produce an intermediate. Suppose with that first collision, NO2, 1 molecule here, collides with an F2 and they produce NO2F. So in other words, I'm going to take off a fluorine, and NO2F would now be breaking its bonds, and what we've got is an intermediate. So just by thinking through what's happened, this would be sitting on top of that energy barrier up at the top of the hill. This isn't a product, and yet it is made in that first elementary step. If I look at the next step, this fluorine atom then collides with the second unit of NO2, giving us our next product. So again, if I break the bond, snapping on the next fluorine, we now see on the product side 2 molecules of NO2F. It happened in a 2-step collision, where the first step, the slowest step, came directly from the rate law. In a faster step, which just means it had lower activation energy, the product then was formed with a second unit of NO2F. Thinking about this energy diagram, if the first collision was the slowest, I had at the top of the larger activation energy hill